Electric Field, Part 4. Today we're going to study the electric field between two charged plates separated by a certain distance. A and B are two plane conducting plates separated by a distance d. The plates are subjected to a voltage supplied by a generator. When we close the switch, the positive pole of the generator will attract the free electrons of the conducting plate A. The electrons will circulate in this direction. The electrons will be repelled by the negative pole of the generator and will move towards the plate B, where they accumulate like this. The plate A is initially neutral. Upon losing its electrons, it becomes positively charged. On A, there is a uniform distribution of positive charges. On B, there is a uniform distribution of negative charges. What is the electric field at a point M between these plates? How can we determine this field? Each punctual charge creates at M an electric field. For example, this point charge creates at M a field that is directed outward since it's positive. This is E1, for example. This point charge creates at M an electric field, E2, for example, in this direction. This creates a field, E3. This creates a field, E4, and so on. This, for example, a field like this. If we do the vector sum of all these fields, we notice that the electric field that results from this plate is directed in this way. This is the resultant electric field created by plate A. Now let's move on for plate B. At the same point M, this point creates an electric field like this. Let's call it E1 prime, for example. This point creates at M an electric field like this. Similarly, this charge creates an electric field like this. Also, this charge creates its field like this. The sum of all these fields created by plate B at point M is in this direction. Let's call it EB. What is the resultant electric field vector at point M? The resultant electric field vector at the point M is the resultant of the fields EA and EB. Hence, it is in this direction. This is EM. This is the field vector EM. Then, the field vector EM created by the two plates is perpendicular to the plates and is directed from the positive plate to the negative plate. From the positive plate to the negative plate. Let's draw a clearer figure. This is plate A. This is plate B. These plates are subjected to a certain electric voltage. This voltage creates a positive charge on A and a negative charge on B. These plates create at a point M between them an electric field like this. E is perpendicular to the plates, directed from the positive plate to the negative plate. This is E at M. Also at a point N, for example, the electric field is in this direction as well, perpendicular to the plates and directed from the positive plate to the negative one. We can show that all the electric field vectors are equal. E at M is equal to E at N is equal to E. The electric field here is uniform, since all the electric field vectors are identical and their magnitudes are equal. They are equal to U over D, where D is the distance separating the plates. U is the voltage UAB in absolute value, since we're finding the magnitude of E, which should be positive. UAB is an electric voltage which can be positive or negative. So we put UAB in absolute value. This is the magnitude of the electric field created between the plates. This magnitude is due to the superposition of the electric fields coming from the infinite positive charges of this plate and the infinite negative charges of this plate. Determining this superposition is not complicated. We can determine the magnitude of the resultant electric field simply by this formula. Now let's solve an application. We have two parallel plates separated by a distance of 2 centimeters and are subjected to a voltage of 100 volts. These plates will become charged. This one positively charged and this one negatively charged. We need to find the electric field vector at point A, B, and C. That is to say, we have to determine the line of action, direction, and magnitude. Let's start with the magnitude. The electric field vectors at A, B, and C are identical. It doesn't matter at which point. The magnitude of the electric field vector at A is equal to that at B, is equal to that at C. It's equal to U over D. U is the absolute value of the voltage between the plates. D is the distance separating the plates. U is equal to 100 volts. D is 2 centimeters, so 2 times 10 exponent minus 2 meters. The answer is 5,000 volts per meter. Now let's find the line of action and direction of each vector. The line of action of each vector is perpendicular to the plates. Also, each vector is directed from the positive plate to the negative one. This is, for example, the electric field vector at A. This, for example, is the electric field vector at C. This, for example, is the electric field vector at B. All the electric field vectors are parallel and are directed from the positive plate to the negative plate. The magnitude of these vectors is the same and is equal to 5000 volts per meter. It is independent of the position of the point between the plates. It is a uniform field. Now in the second application, consider two horizontal plates that are subjected to 50 volts. The plates are separated by 0.5 centimeters. In the first question, indicate the sign of the charge on each plate. What is the charge of each plate? Part 1. This plate is positively charged since it is connected to the positive pole of the generator. So it has the tendency to lose its free electrons. And the other one will gain the electrons. This plate becomes negatively charged. The plate P1 will be positively charged. The plate P2 will be negatively charged. The plate P1 is positively charged. The plate P2 is negatively charged. Part 2. Determine the electric field at A and B, then draw it. A and B are found between two charged plates. Then the field created at B or B is that coming from both plates. The plates create an electric field that is perpendicular to the plates. And it is directed from the positive plate to the negative one. From the positive plate to the negative plate. This is the electric field at point A. Similarly, this is the electric field at point B. These two fields have the same magnitude, since the parallel charged plates create a uniform electric field E between them. That is to say, all electric field vectors inside are parallel and have the same magnitude. What is the magnitude of the electric fields at A? EA is equal to that at B is equal to E is equal to the voltage between the plates over the distance separating the plates. The absolute value of the voltage between the plates is 50 volts over the distance is 0.5 times 10 exponent minus 2 meters. E in this case is equal to 10,000 volts per meter. The magnitude of the electric field between the plates is always constant, directed from the positive plate to the negative one. Part 3. At A, we place a punctual charge Q1. This is where we place Q1. And at B, we place another punctual charge Q2. We need to calculate the magnitude of the electric force acting on each particle, then draw these forces. In the electric field, we place punctual charges. The force acting on the charge Q1 is F1. It is equal to Q1 multiplied by the electric field. F equals to Q times E. When a charge is placed in an electric field, hence the charge is subjected to an electric force F equals to QE, Q1 times EA. F1 and EA are proportional vectors. That is to say, they are parallel. But since Q1 is positive, hence F1 and EA are parallel and have the same direction. F1 is drawn like this, parallel and has the same direction as the electric field. The magnitude of F1 is Q1 in absolute value multiplied by EA. 10 exponent minus 9 multiplied by 10,000. The answer is 10 exponent minus 5 newtons. Now let's determine the force F2 acting on Q2. Q2 is found in the field EB. F2 and EB are collinear vectors. Since they are proportional, Q2 is negative. As a result, F2 and EB have opposite directions. F2 is directed like this. The particle Q2, and when placed in the electric field between the plates, will be subjected to an electric force F2 opposite to the field, since Q2 is negative. But Q1, when placed in the field between the plates, is subjected to a force F1 having the same direction as the field, since Q1 is positive. The magnitude of F2 is the absolute value of Q2 multiplied by EB. Minus 2 times 10 exponent minus 10 in absolute value multiplied by 10,000. The result is 2 times 10 exponent minus 6 newtons. This is the magnitude of F2.